This is section 4.5, but we will talk just about the relative rates of growth. And this part of the section will help us to evaluate the limits at infinity of a certain function, especially of the functions that create an indeterminate form, infinity over infinity. Infinity over infinity. We remember this. One function goes to infinity, another goes to infinity, but we can definitely use our intuition, our educated intuition, and apply the growth rates. Which function grows faster, which function grows slower, who is winning, and what is the final answer. Let's see. So we can discuss how function behaves as x becomes larger. And we will look at, we will only investigate as x goes to the positive infinity. Because we do have to be quite confident, limit as x goes to the infinity, positive infinity. We may still have some arithmetic, negative, positive in our formula of the function of the ratio, but we will just, limit will be at infinity, x will be at positive infinity, okay? And at first we can see this, okay? But let's try to compare function f and function g. Let's pick some of the functions. My example number 1 is trying to compare power function like x to the power of n, for instance, okay? Or the exponential function a to the power of x. Yeah, x is in the exponent. Which of these functions is approaching infinity faster? Yeah? We know that both of them goes to the infinity. Okay, what I did just a numerical like approach. Let's look at this. Oh, lots of numbers. Oh, too fast. I took quantity, like I evaluated both of the functions at 100. For the function x to the power of 10 and 10 to the power of x. So in power function, when I evaluate, I substituted 100. 100 to the power of 10 is 10 to the power of 20, because we have 2, the 10 squared, 2 times 10 is 20. 10 to the power of 20 is basically that number. It's 21 digit, 1 and 20 zeros. Okay, we can imagine this number. Let's look at what happened with the exponential function. 10 to the power of x, 10 to the power of 100. 10 to the power of 100 is that funny number, which actually is 101 digits. You may notice which number is bigger, which function will grow faster. Yeah? The growth rate of the exponential function is much faster than the power function. Now I can show you this. Yeah, we know this, we did this in our, in the previous lessons, but just to confirm and just to show you. And I also did the same for the 1000. Instead of x, I did substitute 1000, it's supposed to be 1000. 1000 to the power of 10 is 1000 is 10 cubed, 10 to the power of 30, 31 digit. For the exponential function, 10 to the power of 1000 will give us 1001 digits number, much faster. That's one more time, the summary. Exponential functions grow much faster than power function. They will always win. Doesn't matter what is the exponent and what is the power. Like for instance, I can take 2 to the power of x. It's greater than, this could be different power. Let's say even like, I don't know, 10,000. Yeah, please do not be like misled by the big power. No, the power maybe at some point for the couple of beginning numbers, like small numbers, maybe x to the power of 10,000 will be greater, will be above. But at infinity, for the huge number, for the x value approaching positive infinity, 2 to the x will always win. Yeah? In general, exponential functions winning when competing with power function. Okay, Another example, the comparison of exponential and logarithmic. Yeah, we probably know the answer. It's not, I can even put the inequality. Exponential function at infinity goes to the infinity, and e to the x goes to the infinity. Logarithmic function ln of x at infinity also goes to infinity, but we know which one is slower, which one is faster. I do have the graphs, and we can see right away e to the x is like not even waiting for a couple of inputs. It's right away really high, really high. Logarithmic function, we need lots of input. We need lots of to actually rise a little bit. Both of them are increasing, both of them are approaching infinity, but exponential is much, much faster. I do have a couple of numbers to compare and maybe to think about this. For instance, looking at like trying to not figure out, trying to actually convince you, that e to the x, the exponential function, grows really fast. Let's think about the distance. When we evaluate e to the power of 3 inches, that's when we will just move 3 inches along the x-axis. The height, the value, the output is 20 inches. You can check e to the power of 3. When I substitute 10 inches, what will be the value? We can see we're just moving 7 inches more from 3. You may think it will be quite high. Are we going to reach the ceiling? I was looking for that word. Are we going to reach the ceiling if we like sitting in the room at our desk? Probably even higher, 1/3 of the mile. Believe it or not, only 10 inches input, the output, the height is 1/3 of the mile. And I don't even have a room. And interesting thing, 44 inches, we will move again, 44 inches, how small the input is. This will be unbelievable. 2 million light years. Whatever this means. And the nice number that always you will have this in all of the stories about how fast exponential function is growing, 64, e to the power of 64. You can type in your computer, your calculator, probably you will get an error. This one, it will be, we have to climb, we have to find the ladder and climb 13 billion light years. Approximately this number is like, we will climb, probably we need a plane or maybe some space shot. We will reach the edge of the known universe. Whatever is defined as a known, but that's what we will do, okay? It's extremely big number, and only 64 inches, not even thinking about huge numbers. And this value would be the edge of the known universe. And just to tell you, the light years is how long the light has traveled during 1 year. We know this from physics class. Okay, that means we can see how fast. No, I don't think logarithmic function can compete, because logarithmic is actually the inverse, the other way. In order to reach 64 inches, if I will change the units, of course, then how far the x must be? It will be that value. We have to go along the x-axis, like the different direction, horizontally, it doesn't matter, because the earth is circle, kind of. Then we will go, we will touch the edge of the known universe here, this direction. Maybe I can say east, not north, and only 64 inches if we will be the height. We will only climb this. Okay, that's we are confident that logarithmic function, or maybe I can say exponential, any exponential function with a greater than 1, of course, it's always faster than logarithmic function. Ln of x, not ln of n. Okay, now let's look at this definition. We probably know this definition because we were using a lot. if, this is missing, if one of the function grows faster and we're looking at the ratio to computing the limited infinity of the ratio of these functions, we know what to expect. That means if f grows faster and is placed in the numerator, the limit will be infinity. If f is placed in the denominator, the limit is 0. And the same for this one. F grows faster, but it's just the same thing, but I placed faster function in the denominator. Denominator is with, oh, no, f grows slower. Oh, no. Oh, okay. Probably I just need one example. F grows slower. Because yes, how we can have infinity? F is slower than G. G is winning. Yes, G is winning. If the numerator is winning, always infinity. If the denominator is winning, it's 0. Okay, so we can see how we can. Okay, and then I have one more. If both of the functions, like the relative rate of growth is the same, they approaching like infinity at the same manner, the same speed, then we know that we will have just the ratio of the coefficients. Yeah, like we will have a finite number, not 0, not infinity, of course, but finite non-zero number. Okay, we know this. And now, for instance, when we would like to compare natural log and power function, because we didn't do this comparison. One of the way to check, I can create the limit of the ratio. And we know, of course, I can show, oh, I didn't write this, natural log of x is slow function comparing to any power. I can put n. N could be any positive. Yeah, n is any positive number. Any power. This one is 1, but even if this will be square, cube, 4th, 5th degree, 10th degree. We know, but if we know that the denominator is winning, yeah, we expecting this limit to be 0 based on the previous definition or just based on the previous knowledge. What we can quickly do, since this is infinity over infinity, let's use our new tool, the L'Hopital rule, and let's prove it. Ln of x derivative is 1 over x. This one is 1. When we simplify, we will have 1 over x, 1 over big number. 1 over big number is a small, yes? That 0 is proving that x grows faster than ln of x. Denominator grows faster. Okay, another comparison. Now, x and e to the x. No, nobody can race with e to the x. Maybe one type of the mathematical expression, but not many, definitely not x. We can also try to create a limit. Either way, e to the x over x or the other way. We know that I typed this. Oh, why I didn't type this? We know that e to the x is much faster than any power function. Okay, positive numbers. Then we're expecting this answer to be infinity, right? Let's prove it. Limit as x goes to the infinity, derivative of e to the x is e to the x, derivative of x is 1. And we remember we talk about this, e to the x never goes away. We can differentiate infinitely many times and we will always have infinity. Yeah, actually this is infinity. E to the x at infinity is infinity. If this limit is infinity, we know that function from the top, numerator is weak, yeah? But we knew it this way. And just to clarify it, when you have limits at infinity, please use this relative rates of growth. Yeah? You can give me the answer right away. You can just say, oh, because of the growth rate or relative rates of growth, yeah, that's the answer. Yeah, you don't have to apply the L'Hopital rule. I'm just applying now to prove it. And now, now is interesting. E to the x and 2 to the x, two exponential functions with different base. Limit as x goes, for instance, this. But we remember this is quite, and now, I mean, not even, okay, I'm trying to use the algebra. Okay, I'm trying to use the algebra. We can compare, I can explain my, reasoning for my first step. But of course, if the base of this exponential form is greater, then that exponential function grows faster. E to the x, 2 to the x, e versus 2. I think e is greater than 2. Then e to the x grows faster than 2 to the x. Numerator is winning, is infinity. Okay. I was also, but that's the same thing when we have like, let's say some number r to the power of x. If this r number is between -1 and 1, like a fraction, fraction less than 1. If r is between -1 and 1, small number between -1 and 1, always the limit at infinity will be 0 as x goes to the infinity. But if r is greater than 1, that limit will go to positive infinity. Let's assume that we have positive number. We will not involve negative. That means if this r is less than 1, like a fraction, proper fraction, less than 1, always the limit will go to 0. But if that r, that base of this exponential is greater than 1, and that's the case, e over 2 is greater than 1. And then we taking to the power of x, of course, this will be infinity. But this is just different, more algebraic approach. We know that if the base is greater, the entire exponential function grows faster. And that's it. Okay. That means, yes, this is, of course, infinity because e to the x grows faster than 2 to the x. Okay, we have another comparison. Now, we're supposed to not see this. Now, which function grows faster, x or 2 to the x? X or 2x? I know that we have the moment that we would like to say 2x, but we may see the main function is the same. The easy way is to do the same thing what we did for the previous exercise. Let's create a ratio, and we know that this limit is 2. If the limit is non-zero finite number, these functions are like comparable. They're growing, the relative rates of growth is the same. We do have a certain ratio too, or maybe 1/2, if I will create the fraction other way. But it's not 0, not infinity. None of them, x or 2x, they will be at infinity. Doesn't matter if it's infinity or 2 times big number or 2 times big number. It's a still big number. That means that's two linear function grows at the same rate. Logarithmic functions with different base. You can see, yes, it's similar situation like two linear function. That base for the logarithmic doesn't matter, because we may see the input, it's still the same, it's xx, and that doesn't matter. We can try, I didn't type, okay, we can try to compute a limit. Let's pick some numbers, 2 maybe and 3. And at this infinity of infinity, we can go through the L'Hopital rule, but we may try to use the formula for changing the base. Are we remembering the formula? When we have log base a of b, I can change for the log, b will stay, log, and a will become here. And that base could be any number. Of course, base must be always positive, never 1. That means this is the changing base of the logarithm formula. Let's change. That means log base 2 of x, I will change for ln of x, ln of 2. Log base 3 of x, I will change for ln of x, ln of 3. We can see x stays, 2 will become the input. X stays, 3 will become the input. And what is happening? Let's flip this. Natural log of x, natural log of 2, multiplying by the reciprocal, and we can see they are the same function, just a finite number, not finite number. If we're getting non-zero finite number from that ratio, both of them are like having the same, the rate of the growth rate is like the same, they are comparable. And now I have a theorem that we also were using a lot, because when we have, let's look at this, the ratio of the same function, the answer will be just the ratio of the leading coefficient, k over 1k. Now, the theorem 2, when we have more than one function in that ratio, like for instance, we have f plus g, we know that we're looking for the leading function. This function grows faster, then this is the leading function. The rest of the functions are not important, because you can see algebraically, when I divide everything by the fastest function, this will go to 0. That's the reason that it's not important. So when we have leading function, we're just looking at the leading functions. Please remember, if you have huge, long, like ratio, rational function with the complicated expressions, and we're looking for the limit at infinity, please just spot the fastest function and compare them. Okay? Because we can see f of x over f of x, 1 over 1, 1. I mean, that's the theorem we're using a lot, but just as a reminder. And let's finalize this with this. I have I think 2 or 3 problems. And and we will be done. And your homework assignment will be like so easy to complete. Okay, limit at infinity, and let's look at all of this. I will not even read all of this expression, but I have to pick up the fastest function, the leading function. On the top is this one, definitely. X to the power of 1000. In the denominator is e to the x. And e to the x, 10 to the x to the power of 1000. We know that exponential function grows faster, denominator grows faster, 0. By, and we can say by relative rates of growth. Okay? And if you have this question on your assignment, you can just type this and that's done. We can see how nice, one question done in less than a minute. Another one, interesting. The leading function, because it's limited infinity, of course. The leading function is square root of x squared. The rest of them are not important because algebraically they will become 0. And the leading function is x squared. Square root of x squared at positive infinity, we can cancel out both of them, the squared and the square root. And I can still simplify, and I can get 1 over x, but looking at x and x squared grows faster. Denominator grows faster, 0. By the relative rates of growth, okay, we use the relative rates of growth. Relative rates of growth, okay? Oh, another one, limited infinity. 3 to the power of 2x looks like that exponential function. It's a leading function, and 4 to the x. And we may notice this is actually greater because it's 9 to the x. Numerator is winning, the answer is infinity, and we can say we use relative rates of growth. Do I have one more? No, I don't have it, but let's finalize this quick and nice session. with this relationship. And what we can see, we see exponential function a to the x, b to the x. Of course, b to the x will grow faster because b is greater number. And then slower function than exponential are the power function, and they also compete between each other, depends on the of that power. If b is greater, like b cube, x cube, x to the power of 4, 5, will grow faster than slower number, like x to the power of 2, 3, respectively, yeah, for the inequality. And then logarithmic will stay at the end. And even if I make the combination, the composition function logarithmic with logarithmic, even slower. Okay, but that's what I was saying. One little guy here at this point, it's faster than exponential. It's like function taken to the power of another function. Okay, but I don't know if we will have this a lot, but just, yes, for our information, we definitely have to focus on this relation. And please use it, please use a lot to evaluate limits at infinity, just to speed up the process and applying the relative rates of growth. Thank you.